Hello friends, this is Nishan presenting to you a few very interesting examples of acid-base disorders. In this video, I am going to follow the same approach I followed in my previous video. So I would recommend you to watch my previous video as well, just to get a better idea of the foundations. I am providing link to that video in the description section of this video. So let's get started. These are my references for this video. Before jumping into solving questions, let us briefly review what we have learned in the previous video. So the normal values, there are four important normal values that you need to remember: pH, PCO2, bicarb and anion gap. And the values of are given as follows. pH is 7.38 to 7.42, PCO2 is 38 to 42, bicarb is 22 to 26. Anion gap however varies with laboratories, but the reference range is taken as 8 to 16. For the purposes of calculation, we use the average values like pH of 7.4, PCO2 of 40, bicarb of 24 and anion gap of 12. So if we look at the stepwise approach, there are two things that we should look at. Number one is pH, number two is PCO2. We should look at the direction of their change. If one of them is abnormal, it means that there is an acid-base disorder. Now, how they change, that determines the whether the disorder is acidosis or alkalosis and whether the disorder is respiratory or metabolic. If the pH increases and PCO2 increases, or if the pH decreases and PCO2 decreases, that is the change in the same direction, the primary disorder is metabolic. It can be acidosis, it can be alkalosis depending on the change of pH. Then if pH increases and PCO2 decreases, or if pH decreases and PCO2 increases, the disorder is respiratory. How do we remember this? So I am going to give you two words. Number one is respiratory and number two is reverse. There are first two letters of these are RE. So the direction will be reverse in respiratory disorders. Once you have figured out the primary disorder, you need to start looking for the compensation, if the compensation is appropriate or if there is a second disorder. How do you look for it? So in metabolic acidosis, if the primary disorder is metabolic acidosis, we have something called as Winter's formula, in which we calculate the expected value of PCO2 by 1.5 times bicarb plus 8 plus minus 2. This plus minus 2 is there as this formula gives us a range of expected PCO2. In metabolic alkalosis, we know that in metabolic alkalosis, the bicarb concentration increases. So for every 1 milliequivalent rise in bicarb concentration, PCO2 should rise by 0.7 millimeters of mercury. For respiratory disorders, it is slightly difficult to understand. So what I would recommend is to just remember these values. Acute respiratory acidosis, for every 10 millimeters of mercury rise in PCO2, the bicarb should rise by 1 milliequivalent. Then in chronic respiratory acidosis, for every 10 millimeters of mercury rise in PCO2, the bicarb should rise by 4 milliequivalents. In acute respiratory alkalosis, for every 10 millimeters of mercury fall in PCO2, the bicarb should fall by 2 milliequivalents. And in chronic respiratory alkalosis, for every 10 millimeters of mercury fall in PCO2, the bicarb should fall by 4 milliequivalents. Mind you, what I am saying that it should fall by, I mean that under normal circumstances. If there is any deviation from this pattern, it means that there is a second acid-base disorder. When you use the formulas on the previous page, you will get expected value of PCO2 and expected values of bicarb. And when you look at the given ABG, you will get the measured value of PCO2 and measured value of bicarb. So by looking at them, you can just figure out if there is a second acid-base disorder. If there is the measured PCO2 is more than expected PCO2, that is there is more CO2 that is retained. Can you guys remind me of a condition in which there is more CO2 retention? Yes, it is respiratory acidosis. Then if the measured PCO2 is less than expected PCO2, that is the PCO2, that is the CO2 concentration in the blood has decreased, It means that we are washing out more CO2, and it basically means that there is a coexisting respiratory alkalosis. So, look, talking about bicarb, if the measured bicarb is more than expected bicarb, that is, there is more bicarb, can you guys remind me of an acid-base disorder where we retain bicarb? Yes, that's correct. It is metabolic alkalosis. So there is a coexisting metabolic alkalosis. And when the measured bicarb is less than expected bicarb, it means that we are losing bicarb. And can you guys remind me of a condition where we lose bicarb? Yes, that is correct. It is metabolic acidosis. So there is a coexisting metabolic acidosis. This is how you figure out whether there is a second disorder present or not. Case number one, we have someone with suspected opioid overdose whose ABG is given as follows: pH of 7.22, PCO2 of 60, and bicarb of 26. I'm just going to take a 1 second pause for you guys to pause the video and solve this on yourself first. So looking at the solution, we have a pH of 7.22, which itself tells us that the pH is less than 7.38, so there is acidosis. Then we have a PCO2 that is more than 40 millimeters of mercury. So PCO2 of more than 40 millimeters of mercury means the PCO2 has risen and the pH has fallen. So when the pH decreases and PCO2 increases, that is the change in opposite direction, the disorder is respiratory, and we have figured out the primary disorder to be acidosis, so the disorder becomes respiratory acidosis. Patient has opioid overdose, so most likely the setting is acute, so the diagnosis becomes acute respiratory acidosis. For acute respiratory acidosis, we know that for every 10 millimeters of mercury rise in PCO2, the bicarb should rise by 1 milliequivalent. Here, the rise in PCO2 is 60 minus 40, that is 20. So we can figure out that the bicarb should rise by 2. That's correct. So in this case, we have bicarb of 26, and the expected value of bicarb is also 24 plus 2, that is 26. So there is no additional disorder. So the diagnosis becomes acute respiratory acidosis only. Looking at the second case, interpret the following EBG of someone with suspected pulmonary embolus. The pH of 7.58, the PCO2 of 25, and the bicarb of 21. I'm going to take a 1 second pause for you guys to figure it out. For this, the pH is 7.58, which is more than 7.42, which tells us that there is alkalosis. Then looking at PCO2, the PCO2 is less than 40. This tells us that the pH has increased and PCO2 has decreased, which means the primary disorder is respiratory, which in turn is respiratory alkalosis. The setting is most likely acute as the patient is having pulmonary embolus. So the primary disorder is acute respiratory alkalosis. Solving for compensation, for acute respiratory alkalosis, we know that for every 10 millimeters of mercury fall in PCO2, the bicarb should fall by 2. In the given case, bicarb is 21. So, and the PCO2 is 25. So PCO2 has fallen by 15. So 10 is to 2 means 15 is to 3. So the bicarb should fall by 3 milliequivalents, which is 21. So 24 minus 3 is 21, and the given value is also 21, which tells us that there is no second disorder and there is only one disorder, that is acute respiratory alkalosis. Next question, interpret the following ABG: pH of 7.20, PCO2 of 30, and bicarb of 10. So I'm going to take a 1 second pause again. Now the pH of 7.20 tells us that this pH is definitely less than 7.38, so there is acidosis. The PCO2 of 30 is definitely less than PCO2 of 40, so the pH has decreased as well as the PCO2 has decreased, When they change in same direction, the disorder is metabolic. So the primary disorder becomes metabolic acidosis. Acidosis. To look for compensation, we use the Winter's formula, which is given by expected PCO2 is 1.5 times bicarb plus 8 plus minus 2. If we substitute these values of the given ABGs in this formula, we get the expected value of PCO2 to be 21 to 25. However, in the given ABG, the PCO2 is 30, which tells us that there is more CO2 retention. And this tells us that the second disorder is present, and it is respiratory acidosis. That is why the complete diagnosis becomes metabolic acidosis and respiratory acidosis. Interpret the following ABG: pH of 7.27, PCO2 of 24, bicarb of 9, sodium of 130, and chloride of 100. It is very important to remember that whenever these people are giving you the value of sodium and chloride and bicarb in the given ABG, it means that they expect you to calculate the anion gap. So let's solve for this ABG. Given ABG, pH is 7.27, which is less than 7.38, which tells us that there is acidosis. The PCO2 is 24, which is less than 40. So pH has decreased and PCO2 has decreased, hence the primary disorder is metabolic, and perhaps it is metabolic acidosis. Calculating for the anion gap, sodium of 130, chloride of 100, and bicarb of 9, the anion gap comes out to be 21. Can you guys remind me what is the normal level of anion gap, normal value of anion gap? Yes, it's 8 to 16, which tells us that the anion gap is increased in this case. Presence of metabolic acidosis in presence of an increased anion gap gives us a diagnosis of high anion gap metabolic acidosis. Lactic acidosis, ketoacidosis are few examples of high anion gap metabolic acidosis. To calculate for compensation of metabolic acidosis, we know that we calculate it by Winter's formula. We just saw it in previous example. So expected PCO2 in this comes out to be 19.5 to 23.5. So expected PCO2 is approximately equal to the measured PCO2, like 24 and 23.5. It's approximately equal. So there is no additional disorder, and the only disorder that is present here is high anion gap metabolic acidosis. Then the next ABG, the pH of 7.29, the PCO2 of 33, bicarb of 17, sodium of 129, and chloride of 102. Again, they have given sodium, chloride, and bicarb values, so we have to calculate anion gap. So let's take a 1 second pause for you guys to solve this on your own first, then we can solve it together. So in this case, the pH is 7.29, which is less than 7.38, which tells us that this is acidosis. PCO2 is less than 40. So the pH has decreased, the PCO2 has decreased, they change in same direction, which tells us the disorder is metabolic, and it is indeed metabolic acidosis. Anion gap, however, in this case is coming out to be 11, like 129 minus 102 minus 17 is coming out to be 11, and it is well within the normal range of anion gap. So the disorder becomes normal anion gap metabolic acidosis. Can you guys remind me a few examples of normal anion gap metabolic acidosis? Yes, that's correct. Basically, all the renal tubular acidosis are normal anion gap metabolic acidosis. Then looking for compensation in this case, again, metabolic acidosis, we have the Winter's formula. If we substitute the values in the given ABG, it comes out to be 31.5. The expected PCO2 comes out to be 31.5 to 35.5. In this case, it is 33, which is well within this range, which tells us that the only disorder present in this case is metabolic acidosis. The next ABG, so somebody with chronic CO2 retention has this ABG: pH of 6.95, PCO2 of 70, and bicarb of 18. I'm going to take a 1 second pause again for you guys to solve this. So solution for 6.95, pH of 6.95. So just one pearl that I would like to drop here is that when you see a pH of less than 7, or I would say less than 7.1, you should start suspecting that there are probably two acidosis working together. So in this case, the pH is less than 7.38. Again, our basic algorithm, there is acidosis. The PCO2 is more than 40. So the pH has decreased and PCO2 has increased. Hence, the primary disorder is respiratory, and indeed it is respiratory acidosis. This patient has chronic CO2 retention, most likely a case of COPD. So the diagnosis becomes chronic respiratory acidosis. However, we are not done yet. We have to calculate for the compensation as well. So looking for compensation, in a patient who has chronic respiratory acidosis, we know that for every 10 millimeters of mercury rise in PCO2, the bicarb rises by 4 milliequivalents under normal circumstances. In this case, PCO2 is 70, that it has increased by 30. So for that, the bicarb should rise by 3 times 4, that is 12 milliequivalents. So the expected bicarb is 36, that is 24 plus 12 is 36. However, in the given case, we have the bicarb value given as 18, which is much lower than the expected bicarb. So remind me of a condition in which we are losing bicarb. Yes, that is metabolic acidosis. So in this case, we have a additional metabolic acidosis, and the complete diagnosis becomes chronic respiratory acidosis with metabolic acidosis. Going to the next example, pH of 7.60, PCO2 of 40 and bicarb of 35. The pH is 7.60, which is more than 7.42, which tells us that there is alkalosis. PCO2, however, is normal in this case, so we will have to look at another value, that is bicarb. The bicarb is 35, which is much more than the normal value of bicarb, that is 24. So remind me of a condition in which we retain more bicarb, or we have more bicarb as compared to normal. That's correct, it is metabolic alkalosis. So the primary disorder in this case becomes metabolic alkalosis. Looking for compensation, in this case for metabolic alkalosis, we know that in metabolic alkalosis, for every 1 milliequivalent rise in bicarb, the PCO2 should rise by 0.7 millimeters of mercury. So in the given case, the PCO2 should rise by 7.7 as calculated here. Expected PCO2 becomes 40 plus 7.7, that is 47.7. However, in the given case, it is found to be 40, which means that the more PCO2 has been washed out, that is measured PCO2 is less than expected PCO2, hence there is a coexisting respiratory alkalosis, as we have lost more PCO2, probably due to hyperventilation. So the complete diagnosis becomes metabolic alkalosis with respiratory alkalosis. Last one for this video, the pH of 7.41, PCO2 of 55 and bicarb of 30. Yes, the pH is well within normal range, but if you remember from my first video in which I said, like, even if the pH is normal, it doesn't rule out an acid-base disorder. This can still be a mixed disorder. So the next step becomes looking at PCO2. In this case, the PCO2 is 55, which is more than 40, which tells us that the primary disorder is respiratory acidosis. Now, the pH has normalized, so it is very important to understand that there has to be a coexisting alkalosis of same intensity or of the same strength. However, it is again very important to understand that respiratory acidosis and respiratory alkalosis can't coexist at once. So there has to be a metabolic alkalosis. I'm saying respiratory acidosis and alkalosis can't coexist because a person can't hypoventilate and hyperventilate at the same time. So in this case, the complete diagnosis becomes respiratory acidosis with metabolic alkalosis. So the take-home point from this last example is that normal pH doesn't always rule out an acid-base disorder, especially when it is coming on an exam. You should be very careful before choosing the normal ABG option. That's about it for this video. I will see you guys in the next video. Thank you for watching the video. If you like the video, please like, share, and subscribe. If you have any questions, concerns, or doubts, feel free to reach me at love.intmed@gmail.com. Thank you very much.